In modern software engineering, there is an unwritten rule that dictates almost every code review. If a class or method gets too long, break it down. We are taught to relentlessly divide our logic into smaller and smaller single-purpose components. Yet, enterprise object-oriented codebases, built strictly by this rule, routinely devolve into unmaintainable, fragile spaghetti code. Adhering to the clean code heuristic often makes the underlying logic harder, not easier, to follow. Software design focuses on minimizing the structural friction that makes a system hard to understand and modify over time. While producing working code is the immediate task, the long-term priority is controlling this complexity. Stanford professor John Ousterhout argues that we should prioritize depth over size. To minimize friction, we must rethink our assumptions and focus on designing deep modules. The dogmatic pursuit of tiny single-purpose classes creates a condition Ousterhout calls classitis. Shattering logic into microscopic pieces maximizes the friction between components and actively destroys the system's architecture. Software complexity is structural friction, the dependencies and obscurities that make a system hard to understand and modify. This diagram illustrates change amplification. Explicitly declaring a background color on 50 pages requires 50 manual edits to change it. A shared variable fixes this, but risks unknown unknowns. If a secondary color secretly matches the background, updating the variable silently breaks the layout. We can never eliminate dependencies entirely. They are a fundamental part of software. Our goal is to make the dependencies that remain as simple and obvious as possible. A system's true complexity is the volume of information a developer must hold in their head to make a single modification safely. Total lines of code matter far less than this total cognitive load. Every software module, whether it's a class, a method, or a service, is an economic transaction involving cost and benefit. The benefit is the implementation, representing the complex logic, state management, and functionality the module handles, so the rest of the application doesn't have to. The cost is the interface. This includes the signatures, parameters, and rules the caller must manage in order to use the module. A deep module maximizes implementation benefit while minimizing interface cost, exposing only a fraction of its internal complexity. Conversely, a shallow module provides an interface nearly as complex as its logic, forcing the caller to do the heavy lifting. Classitis guarantees shallow modules. Artificially limiting the size of a class reduces its benefit without reducing its cost, flooding the system with cognitive load. The Unix file I/O system is a masterclass in deep module design, optimized specifically for the most common use case, sequential access. Its incredibly narrow interface consists of just 5 basic system calls: open, read, write, lseek, and close. This tiny interface conceals massive internal machinery. The kernel manages physical disk blocks, thread scheduling, access permissions, and memory caching without leaking details. Contrast this deep architecture with the historical Java class library approach to file I/O, which suffers severely from classitis. Java separated basic file opening, buffering, and serialization into distinct, shallow classes. To read serialized data, a developer is forced to manually wire a file input stream into a buffered input stream, then wrap that into an object input stream. Buffering is a near-universal requirement for file reading. When an API forces a developer to instantiate 3 separate objects to perform a common task, the complexity has leaked directly into the caller's lap. Smart engineers frequently design shallow, leaky modules because of a psychological trap called temporal decomposition. Temporal decomposition involves structuring classes based on the chronological timeline of execution, rather than by the encapsulation of knowledge. Consider an HTTP server project, where developers split network handling into a timeline. Class A reads the raw request from the socket, then Class B parses it. This creates an architectural failure. To know when to stop reading data, Class A must partially parse the HTTP content length header. It has to understand the format just to read it. The specific rules of the HTTP format have now infected multiple separate classes. Designing around a timeline inevitably guarantees information leakage. The exact same data rules will be required at multiple steps, binding separate classes together in a way that makes them extremely difficult to change. Fixing temporal decomposition requires combining chronological steps to completely encapsulate specific knowledge. Fusing the read and parse logic into a single, deep HTTP processor module successfully hides the HTTP format from the rest of the application. Despite these benefits, many startups prioritize speed over encapsulation. They encourage tactical programming, focusing on pushing new features as quickly as possible. This environment produces the tactical tornado, a prolific programmer who pumps out code by ignoring architecture. Ultimately, this infamous move fast and break things culture generates massive technical debt that slows down every engineer who follows. Strategic programming offers a different path, treating clean architecture as a prerequisite for scale. High-quality code and deep modules are viewed as the primary drivers of long-term productivity. Tactical programming is a loan taken against your future velocity. The resulting spaghetti code will eventually throttle the team, making even simple changes difficult and risky. Maintaining a healthy codebase requires a continuous 10 to 20% time investment in proactive design and reactive refactoring on every single task. While tactical programmers usually win the first few months, strategic programmers rapidly overtake them once technical debt begins to compound. Single responsibility signifies that a module owns a complex concept entirely. It must absorb all the necessary logic to shield the rest of the codebase from that specific area of concern. Challenge the instinct to shatter your logic into microscopic, shallow classes. Final success comes from building deep modules. Let them absorb the complexity of the system and present only a simple, powerful interface to the world.